So last time we proved that sine x and cosine x both converge to their Taylor series for all x. So they're identically equal, so mathematically we can interchange them anytime we want, the function for the series. And I'm going to do the same thing for e to the x. The only difference really is I do have to do it in two cases because that bounding part depends on whether x is to the right or to the left of our center. If you recall, sine x and cosine x were nice because all of their derivatives are bounded by 1 in absolute value. So let's look at this as two separate cases. So first of all, let's start with the case of x is less than 0. So I want to set up that same inequality. We know that our error magnitude, because it's an absolute value, trivially is greater than or equal to 0. And remind ourselves that that's equal to, now the n plus 1 derivative. Well, this is nice because e to the x, no matter what derivative it is e to the x. So that's e to the c over n plus 1 factorial. X minus a, well, a was 0, so it's x to the n plus 1. So the key is going to be bounding this e to the c. So let's think about, because x is less than 0, what does that mean? Well, remember we're looking, c is somewhere between x and a is 0. So if this is our x, we know e to the, so there's 0, there's x, and remember c is somewhere in between, some unknown value in between there. But if we want an upper bound, that value there is 1, right? E to the 0 is 1. So we know no matter where c is, that function is always less than 1. So this side actually works just like sine and cosine did because we can use an upper bound on that of 1. So that's less than . And this is just like what we had before for sine and cosine, right? So now it's just our sandwich theorem argument. Limit as n goes to infinity of 0. It's trivial, 0. Limit as n goes to infinity of that is theorem 5. We know that's 0. So that means, at least for negative x's, the limit is x, limit is n goes to infinity of our error magnitude is 0, and that's by sandwich. So pretty similar argument, really, to what we did for the entirety of sine and cosine. So now let's look what changes if we're over on this side. So here we were doing some x on the left, so we knew we could use 1 as an upper bound. What changes over here if x is greater than 0? Well, that statement there doesn't change, right? It's still Taylor's theorem. But it's going to be the bounding, right, that changes. So let's draw our picture if we're on the other side. So if we have some positive x, a is still 0, c is somewhere in between there. Right? This is very similar to the example I did of error bounding, right? We had an x of a half, I think, in that one. But no matter what that x is, there is an upper bound, and the upper bound is whatever that point is, which is whatever e is at x. So I can say that this is definitely less than e to the x over n plus 1 factorial x to the n plus 1 in absolute value. Now this may seem like we've gotten into trouble here because how are we going to bound? It seems like in the previous examples we've been able to get that down to some constant bound, right? But what we have right now is a bound that depends on x. But think about the limit we're going to take. We're going to take a limit where we let n go to infinity. So for any particular x, this is a constant, right? So this will be a different constant for different x's. But when we take the limit, that doesn't change. So let's rewrite this with the e to the x in absolute value is just e to the x, right? So I'm going to write that out front. Okay. So in our argument here, in our sandwich theorem argument, we would have the lower bound, trivially, 0. But what about this thing? When I take the limit as n goes to infinity of e to the x times absolute value of x to the n plus 1 over n plus 1 factorial, for a given x, this is just some number. This expression is headed to 0 by theorem 5. So really, in terms of the limit, this is a constant. So I can take it outside the limit. So it's really e to the x times that limit. But that's that limit we keep seeing from theorem 5. So it's e to the x times 0, theorem 5. And for any given x, that is 0. So we showed that the upper limit, or excuse me, the lower bound heads to 0. The upper bound heads to 0. So put those two together, and you have this statement again. I won't rewrite it since I'm out of room. But now our final conclusion is that the magnitude heads to 0 by sandwich theorem. So it's true on the left. For x is less than 0, you can argue that the error heads to 0. The error bound is slightly different, right? But it does head to 0. Over here, same thing. It heads to 0. Now notice, if you were looking at the accuracy here, the error bound here is much smaller, right? We're able to say that our error is always less than this expression. And x is actually fairly small, right? It's negative, so in absolute value, I guess that would be the same. But this has an extra bit, right? So the error tends to be bigger on the right-hand side than on the left-hand side. But they both head to 0. And that's all that matters. So on the left-hand side, magnitude heads to 0. Right-hand side, magnitude heads to 0. So overall, no matter what x is, e to the x does equal its Taylor series. We can erase that question mark. It is actually true. So now we've got three things. E to the x, sine x, and cosine x. Those will be our big three. When we move on to applications and start using these, we'll mainly stick with those three functions. So anytime we see e to the x, sine x, or cosine x, we are well within our rights to replace that with the Taylor series because they are the same thing mathematically, because we've proven that their difference is 0.